Hi everybody, it's Mr. Spudik, and today we are talking about current, electricity, voltage, resistance, all that fun stuff. Okay, so here we go, let's get started. Before the first battery, the only type of electricity you could get was really from static electricity. So yeah, you had lightning or you had objects rubbed against each other. There was even a machine that could have two plates basically being spun and would create different static charges. But all that changed when we had Mr. Volta create the world's first battery. So let's check it out. What Volta did was this. He took two different types of metal, copper and zinc, and he placed them in an acid bath. Now, if you want to think about chemistry for a minute, if you place copper in an acid bath, a chemical reaction is going to take place. And that chemical reaction will start to take away electrons from the copper. So if you take away electrons, you have a deficiency of electrons, that means you'd end up with a positive charge on that copper. Now what about the zinc? The zinc will be doing the opposite. When you place zinc in an acid bath, you will get a chemical reaction as well, but now you're going to start gaining electrons. So the zinc would get a negative charge. Okay, so you have these two metals that are in an acid bath. One's positively charged, one's negatively charged. And let's say you place a wire between them. What do you think is going to happen? Well, what do you think? The zinc, the negatively charged metal that has too many electrons are going to start pushing the electrons over to where there's too few, okay, to try to even it out. So you're going to have the negative charge and all those extra electrons being pushed over to where there's not enough electrons, and all of a sudden you have a steady flow of electricity. Now, for a minute, you can think about them as electrons, and there's too many electrons negatively, they go to the positive charge. However, hundreds of years of convention of what the rules we follow as scientists will tell us that we need to follow this too, that current, what we call current, will actually be the flow from positive to negative. Okay, so just follow that rule. Anytime we talk about current, it's going to go from positive to negative. Okay, so that was our first battery. Now, you could do this anywhere too. You could place two different spikes, and you'll see sometimes that there are clocks and other things that will run off a potato or a lemon. And the idea is that you have two types of metal, like copper and zinc, and it's going to create that voltage. Okay, there's actually a good video, which I'm not going to show right now, but there's a really good video that Mark Rober did where he created the world's largest battery and took a bunch of lemons and stabbed them onto basically copper and zinc metal and created this battery for you. All right, now let's talk about some terms. That potential difference, that difference in charge between the positive and negative, the greater that charge, the greater that difference, the more electrons can be pushed through a circuit. So we call that potential difference. The difference between charge, we're going to talk about as the potential difference. But we won't really use potential difference too much. We'll use the word voltage, named after Volta. So when we talk about voltage, that is talking about how strong that battery is and how much it can push electrons through a circuit. Okay, next you need to understand about current, and we'll talk about different types of current, direct current. Right now with a battery, we're going to talk about direct current or DC. All right, so current is how fast those electrons or how many electrons can move through a circuit at one time. Okay, so we already know voltage and we know current. All right, the next one we're going to learn is power, and power is just going to be how much, and we're going to show the equation here in a second, how much voltage and power, how much energy is being used. All right, so let's look at the formula. P equals IV. P is for power, I is for current, V is for voltage. And this formula is used all the time for electricians. Okay, if you have an electrician come to your house, let's say he or she has to run a circuit in your basement, and that electrician is going to use this formula. So what they're going to do is they'll say, all right, well, I know these light bulbs have this much wattage, this much power, this stereo, whatever you're going to plug in, whatever you're going to connect, all these things have power or are going to use power, and he's going to add up all that power. So that would be P in our equation. Okay? Then in the United States of America, we use 120 volts AC. Always. I'll say it again. In the United States of America, we use 120 volts AC. So what we would do, and what the electrician would do, is take the power, divide it by 120, and he or she would get the amount of current, I, that will be running through this circuit. Okay, now if it's a lot of current, the electrician will have to use a thicker wire. If it's less current, the electrician could use a thinner wire, which would save money. Also, if you look in your breaker box, and you're probably in your basement, if you look at the circuit breakers, you're going to see numbers on them. Okay, and those numbers have to do with how much current. So if you see a 15 on that breaker, that means 15 amps can run through that circuit until it's going to pop. All right. If you see another one with 12, that means 12 amps. And so again, that's telling you that if it's going to allow 12 amps to go through, but if there's any more than that, the circuit breaker will pop so that your house doesn't burn down. Okay. All right. So a quick review of the units. Power is measured in watts, just like any light bulb you might see. 100 watt light bulb. Look on the back of any electronics. You'll see how many watts they use. All right. Current is in amperes, and really we're going to shorten that to amps. All right. And then finally, voltage is in volts. All right. Now, I say not all laptop chargers are the same. And this is what I mean. If you look at a laptop charger, okay, you can look. There's going to be some values there. It's probably hard to see anyways. But you're going to see an input and an output. And what that means is this. The input is obviously going to be plugged into the wall, right? And it's going to tell you how many volts. And in the United States of America, it can take 120 volts AC. And we'll get 120 volts when we plug in, okay? But it's going to tell you how much voltage and how much current. Then you have the other end. Here, right? And just because it can fit in your laptop doesn't mean it's the right charger. So how can you tell if it's going to be the right charger? Well, you look on the sticker, okay? And it's going to tell you the output of this charger. And this charger has an output of basically 20 volts and base 6 amps, okay? So 20 volts and 6 amps is coming out of this plug. Okay, so if I want to plug it into my laptop, I better double check my laptop and see if the input of the laptop is going to be 20 volts and 6 amps also, so I don't mess up my laptop. Okay, cell phones used to be this way with all these different chargers, but over the years they've switched it to basically, with smartphones, they have to match up to the computer, and so most chargers will be, obviously you have Apple, which is the lightning cable, and then Android, which will be the USBs, micro USBs. Those are usually both 5 volts. So there's some convention, so it's a little bit safer with phones. It didn't used to be back in the day. Okay. Once again, in the United States of America, you get 120 volts AC. Always, always, always. Now, if you go to Europe, you would see different voltages. Okay, in different countries, they'll have different voltages. Or, in any other continent, you're going to see a different voltage being given to the wall, which is why you have to buy a power converter if you ever travel outside the US to make sure that you're going to get the same voltage and you can use all the electronics that you own. Okay. Now, I'm not going to go through the whole analogy right now, but understand that electricity can be considered like water, okay, for a lot of ways. When we talk about current and current and getting split up with different wires, we could think of it as water too, and that's helpful. But also, you could think of water or current and electricity like a waterfall, okay? So let's pretend you have a waterfall in your backyard with a beautiful pool. I'm going to pretend I have one too. All right. If you wanted to push that water up to the top of the waterfall so then it could fall down, you have to build up pressure, and you'd have a pump, okay? And the pump would have a difference in pressure between where it's shot up here and the water coming in. Well, that's like a battery. The battery is basically building up a difference in pressure in charge between the positive side and the negative side, so that it can push the electrons through a circuit. Okay, now that water, let's say the water's at the top of the waterfall, falls down, right? Obviously. When the water falls down, it's going to lose some energy. It's going to lose potential energy as it falls. Well, that's kind of like when current runs through a light bulb or any other resistor. As it runs through there, it's going to lose voltage as it goes through that resistor. Okay? All right. Now, here's some circuit parts you need to know. A battery, power supply, whatever you want to call it, is going to look basically like that. A long side, a short side, a plus and a minus. Now, some people will say you need to have a bunch of those, long, short, and I don't care. I'll do one long, one short. The long side will always be positive. The short side will always be negative. The resistor, like a light bulb, and really anything in this class will be a resistor, is going to be basically that zigzaggy. And then you always want to draw arrows to show the direction of current. Now, here is our next equation, Ohm's Law. And Ohm's Law is going to be with voltage, current, and resistance. Voltage we know about already. Current we know about already. Resistance is going to be how much it resists the current to run through that circuit, okay, or at least at that point. So any light bulb is going to be a resistor. Or anything else, like I said, you plug in will be a resistor. Okay? And the formula is going to be V equals IR. Voltage equals current times resistance. And you'll just have to do the algebra. You solve for voltage, voltage would be just I times R. If you need to solve for current, it would be voltage divided by resistance. Just doing basic algebra. Okay? And the units for resistance are ohms. All right? Or you can use that fancy omega. And that omega is the Greek letter. Okay, but you can use that for resistance as well. Okay, quick reminder. Again, current runs from positive to negative, always. All right, finally, a quick little note. Understand that it's really current that can hurt you, okay? But it doesn't take a lot of current running through your body for you to have damage, okay? But it's a small number. So what's scarier? If you put a sign out next to a big transformer, you didn't want people to touch it so they didn't hurt themselves, would you say, warning, possibly 0.07 amps? Or would you say, warning, 10,000 volts? Now, it still boils down to Ohm's Law, though, okay? So I could even touch an outlet. Don't do this at home, but if I touched an outlet, it would really hurt. I would get shocked. But if I'm wearing sneakers and I have some decent insulation, that means my resistance would be really, really high. Thinking of Ohm's Law, that means my current would be really low. And it would hurt, but I'd be okay. If I touched an outlet, but I'm standing in a pool of water, or I'm doing something else to really lower my resistance, then the current then would go up, and I'd have a lot of damage, okay? So that is why we have to watch out even just with voltage in our house. Now, luckily in your houses now, anything near water, so in your kitchen or in your bathroom, you can find an outlet that has a little push button on it, okay? And that's called a GFI, and that's a little extra circuit breaker to make sure you don't get hurt near water, especially where the resistances could go down low. Okay, well that's it for me today. Thanks so much for watching, and I'll see you next time.